Hello, and welcome to this virtual presentation for the 2020 High Temperature Plasma Diagnostics Conference. My name is Joe Katz, and I am the Project Engineer and Instrument Specialist for the Transmitted Beam Diagnostic on Omega. This instrument is part of a new experimental platform used to study laser plasma interactions in underdense plasmas. I'll start with a general overview of the diagnostic layout, which is shown here in the title slide. A new Wavelength Tunable drive beam has been added to the 61st beam line on Omega at port P9. This beam line, referred to as top 9, has narrow bandwidth, but has an adjustable wavelength range of a few nanometers relative to the other Omega beams. The Transmitted Beam Diagnostic, or TBD, characterizes the top 9 beam after it propagates through the plasma at TCC. A gas jet is typically used to provide the target material to be ionized. After going through focus at TCC, the top 9 beam expands and exits the target chamber through a large aperture vacuum window. The beam then terminates on a semi-transparent diffuser. Light forward scatters off the surface, allowing a CCD camera and lens to record a time-integrated but spatially resolved image of the beam's spatial profile. A bare fiber pointed at the center of the diffuser collects and transports light to a streak spectrometer that measures the spectral power of the transmitted beam. A sample of the beam is taken before it enters the target chamber and is propagated to the same streak spectrometer and is simultaneously recorded along with the transmitted beam. This allows for direct comparison of the initial and transmitted beam pulse shapes and spectrum. TBD can be used to study a variety of LPI processes such as laser absorption, filamentation, and cross-beam energy transfer. Together with the top 9, TBD provides a platform to validate advanced CBET models and mitigation strategies, such as wavelength detuning. Here's a summary. I went through most of this just now, so I'll keep moving. Here are the individuals that worked on the diagnostic. Let's go over some of the TBD design details. Here's a cross-sectional view of the TBD vacuum window assembly at port P4. The TBD occupies the entire 18-inch Omega port and allows for an f4.5 angular field of view of TCC. The initial f-cone of top 9 beam is f7, so this additional field of view provides a means to observe plasma-induced refraction, beam filamentation, or beam spray. A replaceable deep debris shield sits in front of the vacuum window and protects it from physical damage. Swapping the debris shield prior to critical experiments allows the nominal optical transmission to be restored. A Wollaston prism sits in front of the diffuser and provides a polarization measurement of a 20 mm subaperture of the transmitted beam. The Wollaston splits the subaperture into two beams with a 15-degree angle of separation. The beam footprints have enough space to fully separate before hitting the diffuser. By comparing the relative intensities of these two beams on a point-by-point basis, the polarization state of the 20 mm subaperture can be spatially resolved. The diffuser itself is made of a 500 micron thick optical grade PTFE sheet. Approximately 10% of the light transmits through the material and is scattered Lambertianly off its rear surface. This converts the highly directional top 9 beam to a diffusely scattered surface that can be viewed by multiple detectors. An optics platform located 3.5 meters from the diffuser holds the CCD camera and fiber optic pickoff used to sample the transmitted beam. Light for the streak spectrometer is collected with a bare fiber pointed at the center of the diffuser. At the 3.5 meter standoff, the diffuser plate subtends a 0 to 4 degree angular range. The maximum numerical aperture for this fiber is 8 degrees. Underfilling the NA helps improve sampling uniformity across the diffuser plate, as higher angle rays have reduced transmission through the fiber relative to the central rays. A quartz UV lens is used to image the diffuser surface. It's a commercially available lens assembly that has built-in focus and aperture stop adjustments. A thermal electrically cooled scientific CCD camera records an image. Here's an example of a typical image produced by the CCD camera. On the left is an image taken on a shot with no plasma present at TCC. This allows the TBD detectors to be cross-calibrated to the laser system calorimetry. Because the amount of energy delivered to TCC is known, and 100% of that light passes through TCC when there's no plasma presence, a calibration factor in ADUs per joule can be determined. When using the image magnification information, the local fluence deposited on the diffuser plate can be determined. On the right is an image shown with a shot with plasma present. As you can see, portions of the beam refract as it propagates through the plasma, producing a pattern similar to what is seen at the bottom of the pool on a sunny day. Here's a view of the streak spectrometer used to measure the spectral power of the initial and transmitted beam. Both samples are recorded simultaneously on the same streaked image using a custom-built multi-channel fiber optic input head. The standard spectrometer slit assembly is replaced with a V-block array that positions multiple fibers along the spectrometer's input image plane. The fibers are arranged horizontally along the axis of dispersion, allowing each channel to occupy a different region in the output image plane. You can optimize the spacing by populating the V-groove accordingly. A laser cut slit array positions individual vertical slits in front of each fiber optic channel. This allows optimization of the input slit width. Narrow slits are used for high spectral resolution, while wide slits are used for improved sensitivity and dynamic range. The spectrometer is a 1 meter focal length Zerny-Turner and uses 4,300 grooves per millimeter grading. This provides about 7 picometer spectral resolution. Here's an example of a typical streaked image shown on the left. The input beam channel is at the top of the image and the transmitted beam is at the bottom. 500 micron slits were used for this shot. To give a feel for the statistical quality of the measurement, the color bar is shown in photoelectrons per pixel. At peak intensity, an individual channel has approximately 40,000 electrons in a 100 picosecond time bit. The power of the initial and transmitted beam is shown on the plot on the right. For this experiment, a 500 picosecond duration omega beam was fired into a preformed plasma at time t0. During this time, the top 9 beam was also present in the plasma, and energy was transferred from the omega beam to the top 9 beam via seabed. Once the omega beam turned off, the transmitted beam power returned to its original level. By comparing the input and transmitted beam power, seabed can be measured directly. In this case, about 30 joules of energy was transferred from the top 9 beam to the top 9 beam. Here's a quick slide summarizing some of the factors that influence the temporal resolution of the TBD. There are a couple of things at play aside from the temporal resolution of the streak camera itself. First, there's an optical path length difference accumulated on the way from TCC to the fiber optic pickoff. Rays that hit the edge of the diffuser take about 30 picoseconds longer to reach the fiber than ones that hit the center of the diffuser. Next, there's modal dispersion in the fiber optic. This is mitigated to a certain degree by using gradient index fiber, but over the 30-meter path length that takes to go from the pickoff to the spectrometer, about 45 picoseconds of modal dispersion is accumulated. Next, the spectrometer itself introduces an optical path length difference due to the pulse front tilt at the grating surface. This can be limited to a certain degree by masking off the grating in the dispersion direction. But even when masking the grating to an f100 aperture, a residual 75 picoseconds worth of pulse front tilt remain. Finally, then you can consider the streak camera resolution, which is about 30 picoseconds for a 5 nanosecond sweep. Putting everything together, the total temporal resolution of the TBD is about 100 picoseconds full with half max. Thanks for listening to my poster presentation. I'll leave it here. As always, feel free to contact me with any questions. If you're interested in using the TBD on a shot day, or you're considering building a similar diagnostic at another facility, I'd be happy to discuss any issues that may come up. Thanks for tuning in.